You guys do morning lifts for football?
Yeah.
That's cool.
It's pretty bad. We did 3 sets of 5 for 90%.
On what?
On bench.
Oh, bench press?
Yeah.
Incline or flat?
Flat.
I see.
Yeah, do 90% of your max 5 times.
That's what's up.
That hurt, man.
It's important to get angry.
Well,
that's what my coach would always say.
Honestly,
get mad.
But honestly, like whenever you're lifting weights, it has to be controlled.
Yes.
You really can't get angry.
No,
Because then you look like an idiot to our coaches.
I disagree. I think you can get angry and control it. That's my
No,
opinion.
you can, but it's just like lifting. Like,
It takes practice.
They think it's weird if you get angry at the weight.
Maybe it's because I played football at a secular institution. I don't know. But our coaches will always be like, get mad. Get more mad. I liked it. Anyways, moving on to 3.5, if there is one. If there isn't one, we're moving on to 4.1. Trigonometric graphs and models. Oh, goody. So we're going to find what is the graph of the main trigonometric functions, sine and cosine. So our main goal here today is going to be graph sine of t, which is equal to some f of t, and graph cosine of t, which is equal to our f of t. Okay. So what do we mean by graph? And what do we mean by t business? Recall, t is an element of the real numbers. This mathematical stuff just means t is a real number. And a matter of fact, t is an angle, clearly. T is an angle that we evaluate. Okay. So what we aspire to do is to have some type of graphical interpretation of sine and cosine. Okay. I want to call this y. Okay. Or f of t. Really, it's just the outputs. So the way we do any graph is we create a table. To graph points, we need a table, okay? And we pick specific inputs and calculate the outputs for those specific inputs, okay? So it's a really fun game we play here. Can I scoot a little bit over here? Okay. So I'm going to have to delete this information. All right. So let's pick some values for our angles. Let's say 0, pi over 6, pi over 4, pi over 3, pi over 2. Let's just see what happens there. We'll move on actually to one more special angle, 2 pi over 3. Let's see what happens. Okay. Sine of t at t equals 0 implies sine of 0. Okay. And I can actually scooch a little closer here to this table. Sine of 0 is what?
0.
It's 0. Okay. Sine of pi over 6 is what?
1/2.
Yep. Sine of pi over 4 is what?
2 over 2.
Mm-hmm. Sine of pi over 3 is what?
3 over 2.
Mm-hmm. Sine of pi over 2 is what?
1.
Sine of 2 pi over 3 would then equal what?
3 over 2.
It's going back the way it came. Okay, so now that we've tabulated some values, we're going to go pick these values on our t-axis and our y-axis. We could call it a y-axis. We could call it a f of t-axis. We could call it a sine of t-axis. You're used to x and y. It's the same thing. Okay, so here's my pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3. And now we aspire to plot, and of course 0 is over here. We aspire to plot the output of our function at these various values. It would be helpful if I had a different color. Oh, but all the colors aren't here. That's fine. This shows up pretty good on this chalkboard. So, at t equals 0, sine of 0 is a 0, I put a dot. At t equals pi over 6, I find pi over 6. I go to 1/2, which I haven't labeled this, so maybe put a 1 here, maybe put a 2 here. Yeah, I know. Why would you even go up to 2? This is on a unit circle. Yeah, for real. I don't need to go up to 2. We're on a unit circle, meaning the highest value sine can assume is 1, the radius of the circle. So why don't I just put a big old 1 over here? The sine function will not ever surpass positive 1. Furthermore, it will never dip below negative 1, implying, if you will, that the range of sine of t is this interval of the real line. And we know that the domain, we've discussed before that the domain of sine of t is equal to all real numbers. So now let's go to pi over 6. Let's find pi over 6. What is it? Output of 1/2. So I'll put a dot here at 1/2. I go to pi over 4. I find root 2 over 2. What is that numerically? It's around like 0.7. Root 2 over 2 is approximately like 0.7. So it goes up a little here. Okay. Then I go to pi over 3. It's root 3 over 2. That is approximately, I think I told you root 2 over 2 is what root 3 over 2 is. Actually, I might just check here. What is SQRT 2 divided by 2? Oh yeah, so I was right about that. Root 2 over 2 is around 0.7. What's SQRT 3 divided by 2? That's around 0.86. Okay. I just wanted to give you that information just so you're kind of understanding, oh, that's why root 3 over 2 is a little higher. And at pi over 2, simply it just equals 1. Okay. Then we notice that that has to be the highest it gets, right? That has to be the highest it gets. We know that the range of sine is negative 1 to 1. That is the maximum output for sine. So after that, we expect it to dip below, and it goes back down to where this guy was, except at a new location over here. So all we did was we found some dots. A graph is a smooth, continuous curve. So in mathematics, or actually computer algebra systems like your calculator, your internet graphers, what they do is they find an infinite amount of dots. And so the dots look like they're attached. So meaning that they'll find a point in between here and a point in between here and evaluate the function there. So what we do is we just find some discrete points and then we'll just connect them. But what I'm saying is the way that your calculators work, the internet graphers work, they pick all of these numbers in between here. Not really all of them, many of them. A famous mathematician named Gregor Cantor proved that there is an uncountably infinite many numbers in between 0 and 1. Talking about the different levels of infinities is a class in and of itself called real analysis. I encourage all of you guys to take it. I encourage all of you guys to major in physics and math and take real analysis, which is a math class. Really what this guy showed a long time ago was that there's levels to infinity. That there's different kinds of infinity. That some infinities are actually greater than other infinities. It is mind-blowing. Some infinities you can count, like the infinite amount of integers that there exists, like 1, 2, 3, 4 of Googleplex. Keep going. We can count them. But between 0 and 1, there is so many numbers that we cannot count them. Now, I'm just saying this stuff, but I'm not rigorously defining what I'm saying because that's not what this class is about. Real analysis will rigorously define these things. So I encourage you to take that class. Okay, so then notice that, okay, this graph seems like it's going to dip back down at some point and touch 0, right? And Kinsey won't be able to see because I'm going to be writing off of the board here. Also, feel free to ask questions in chat. But the graph makes a wave-looking thing like that. Why is that? Well, eventually sine is going to touch the 0 point over here. At what point does sine reassume the value 0? Sine of 0 is 0, but there's another point where sine equals 0, another angle. What is it? Pi. Correct. And eventually, it does dip down here to become a -1. At what value? Oh, I can cheat the system here.
Oh, it's 3 pi. No, it's just 3 pi over 2.
There we go. I'm looking for that angle. Here we go. Scoot over a little bit. There we go. 3 pi over 2. That's where it would assume the value -1. You guys see that? Okay. So what about these guys over here? Well, these are for the negative angles. Notice that I shouldn't dip below -1 here. Well, we can go to pi by rotating clockwise by pi degrees, or counterclockwise by positive pi degrees. But we can also go to pi by rotating clockwise by negative pi degrees. So notice that over here, we'd find a negative pi. Why? Because sine of negative pi is what? Well, it's equivalent to sine of negative pi plus a 2 pi, right? Because adding 2 pi to any angle does not change where that angle is. So then that just becomes sine of pi, which is 0. So now we know what am I saying here? This should not be negative pi. It should be negative pi over 2. Of course, that's why you look confused. Over here, it should be a negative pi. That's why you look confused. Yeah. So this argument would apply to this point over here. The argument for that negative pi over 2 is sine of a negative pi over 2 is This one is not as clear cut because notice on the unit circle in terms of rotation, this is positive pi over 2, but this is negative pi over 2. Okay, notice that negative pi over 2 is like in the identical location as what angle? 3 pi over 2, is it not? Negative pi over 2 is in the identical location as positive 3 pi over 2. So sine of negative pi over 2 is equivalent to sine of 3 pi over 2. And that's why we get that equaling -1 thing right here. Right here. So now we know what the graph of sine looks like. Who here has heard of the term sine wave? You guys heard sine wave? Yeah. Where did you guys hear that?
In calculus.
In calculus, you heard of a sine wave? Anywhere else? No. Okay. Yeah, people always talk about sine waves because it looks like a wave, doesn't it? It looks like an ocean wave. Very interesting. Really, that wave-like information is encoded in the parametrization of the y-axis projections of a circle utilizing triangles. Now let's graph cosine. And for cosine, what I'll do is I'll actually graph the negatives by hand so that you see what I'm talking about here. And I don't know where my range is at now, so it's probably around here. Yeah, it's this one. Okay, so let's do cosine. Here's where our graph will be. Which will, unfortunately, probably kind of make me move this over a little bit. And now, when I pick points, I'll pick some symmetrical points about this axis. So, how about I go negative pi over 2, negative pi over 3, negative pi over 4, negative pi over 6, 0, positive pi over 6, positive pi over 4, positive pi over 3, positive pi over 2. Let's pick some symmetrical values. I'm doing this so you see, okay, you can do it this way, you can just graph the positives. Graphing is just up to you. You can determine what part of the graph you want based off of the inputs you're choosing. And clearly, the highest value that the cosine function can assume is +1, and the least value you can assume is -1. So yes, I am intimating that the range of cosine of t is equal to the same range as sine of t. And recall the domain of cosine of t is the same domain as sine t. All reals. You can input any real number into it and it'll evaluate it just fine. Okay, so now let's pick some things. Negative pi over 2, negative pi over 3, negative pi over 4, negative pi over 6, 0, pi over 6, pi over 4. I won't list the rest because we probably know them. So we could just plot it right away. At negative pi over 2, what is the cosine of negative pi over 2? Is it 0?
I think so.
let's think about it in terms of like rotations. So this is positive pi over 2, is it not?
Yes.
Okay. So then negative pi over 2 just goes the opposite way. So negative pi over 2 is equivalent to, in positive terms, positive 3 pi over 2. You can actually attain that answer without geometrical intuition. All you got to do is add a negative pi over 2. You add a 2 pi. Notice that this results with negative pi plus 4 pi over 2, which is, again, 3 pi over 2. So in terms of arithmetic, this makes sense. And in terms of geometric rotations, it also makes sense. It's good when math makes sense in multiple different ways. That means, okay, for sure, what we're doing is logical. It helps your argument when you can show it in multiple different ways. So then, Anthony, I'll have to agree with you that cosine of 3 pi over 2 is definitely 0. There's no x value in the triangle when it's straight vertical like that. So what about the cosine of negative pi over 3?
Which one now?
How do you know that?
Well, regular pi over 3 is 1/2 root 3 over 2. And if you just add 2 pi, you'll basically get the same.
Okay. Let's add a 2 pi. I still don't see it. I'm going to add a 2 pi and we'll see. I get negative pi plus 6 pi, everything divided by 3. That's 5 pi over 3. Okay. But how do we know what you're saying is 100% true? 5 pi over 3. Huh?
That answer is not. That's not true. And actually, it is true because it's the same. It's the same thing. It's the same thing as negative pi over 3. Right?
So yeah. So cosine of negative pi over 3 is the same thing as cosine of 5 pi, positive 5 pi over 3.
Yeah.
But what is that equal to?
1/2.
Okay, I'm going to write it. I'm going to put a question mark on the corner. How do we know it's 1/2?
Because 5 pi over 3 is 1/2, and then negative root 3 over 2. It's in the 4th quadrant.
Okay.
And if so, it's the cosine is positive.
Okay. So you're saying it's in the 4th quadrant?
Yes.
So, okay, I like that. Okay, it's in the 4th quadrant, meaning if this is 3 pi over 2, if I do the 30, 15, 15, 30 rule, then I may discover where it's at if I add 30, 15, 15, 30 to this 3 pi over 2, right? When I first add the 30 to 3 pi over 2, here. Okay, here's what I'll do. Aha! Now I'm not running out of room. Okay, so let's get 3 pi over 2. Adding 30 degrees, which is pi over 6, will get us this next special angle, will it not? Okay. So I multiply top and bottom here by a fancy number 1. So this becomes 9 pi plus pi all over 6, which is 10 pi all over 6, which is 5 pi all over 3. Boom! We got our 5 pi over 3 we wanted here. Is this enough to assert Anthony's claims that it's equal to positive 1/2? Well, actually, it's to the right of the y-axis, so these definitely give us positive values. And yes, at 5 pi over 3, we know that over here cosine is 0, and then over here it's going to have the next highest value, positive 1/2. So yes, this is how we can think about it. But we don't have to guess, and we don't have to memorize. I'm showing you how you can just derive it. I honestly, if you were to just say, what is the cosine of 5 pi over 3? Say the result in like 5 seconds, or else you don't win $1 million. I wouldn't win the $1 million. Because I would be like, oh wait, I need some paper, I need to draw you a circle, I need to figure out geometrically where it's at, I need to add a little piece, and I got it. But at the same time, I don't have to memorize anything. Okay, so the reason this way of thinking, the reason that it has merit is that it's foolproof. Sometimes our memory isn't always 100%, and actually under test conditions where there's a high pressure, sometimes memory can be really hard to access. So if you want to go off memory and some type of step-by-step process that will always work to kind of double check yourself, that is the best way of doing things, correct? So now what is the cosine of negative pi over 4? That's when I go from here, I just rotate to this point right here. This is negative pi over 4. So what do you guys think we're going to get? Do you think it's going to be a root 2 over 2? How could we even see that? Well, we can see that adding to 5 pi over a 15 degrees, notice adding 15 degrees to 5 pi over 3 should give us the next special angle. But furthermore, to negative pi over 4, adding 2 pi should give me the same answer. Multiple ways of doing the same thing. This is the power of mathematics, because if you learn how to do things in a multitude of different ways, you won't get stuck. Because sometimes real life situations require you to actually have to go and reach around to find the solution. Okay, so let's see what's going to happen here. Multiply top and bottom here by fancy number 1. So I get this is 20 pi plus a pi all over 12. This is 21 pi all over 12. What does this reduce to? What?
Pi over 3.
Pi over 3?
4 pi over 3.
Oh, 4 pi over 3.
Yes.
Yeah. Because 21 is 7 times 3. 12 is 3 times 4. Cancel out 3, so I get 4 pi over 3. Let's see if this works here. I hope that this gives me 4 pi over 3. Because if it does, pardon me? I hope this gives us 4 pi over 3 just like that. Because then we will be 100% sure that what we're talking about really is working. Okay? So this is over 1, so I multiply top and bottom by a fancy number 1. So I get negative pi plus, that's an 8 pi, everything over 4. So 7 pi over 4. Well, what happened here? So notice this is 21 is 7 times 3 times pi over 3 times 4. Cancel, cancel. We should have had 7 pi over 4.
Yeah.
Not 4. It's okay, man. That's okay.
It's early.
Yeah, it's fine. It happens. But yeah, but I was just like, oh yeah, they should be the same, and I noticed that, oh wait, they're not equal the same. I know what I'm saying is correct. So there must have been some type of like arithmetic error. Okay, so notice, oh wait, this should say 4. Right? I cancel out the 3's, the 4 should remain there. And so they agree. As they should, they agree. So we can actually safely assume that is root 2 over 2. Okay. So then, what's the cosine of negative pi over 6? And cosine of 0. And cosine of positive pi over 6. And you know the drill. Time to graph. Whoa. So, what is cosine of negative pi over 2? Well, over there, our tabulated result shows that it should equal 0. I put a dot. I go to negative pi over 3. It should equal a half. Well, I go over here. I put a dot at one half. So you notice that this is like a half. I go to negative pi over 4. I notice that that should equal root 2 over 2. That is like up here. So I put a dot. I go to negative pi over 6. I notice that should equal root 3 over 2. I go over here. I put a dot. I go to 0. That should equal 1. I go over here. I put a dot. I go to pi over 6. That should equal root 3 over 2. I go to here. I find root 3 over 2. I put a dot. I go to pi over 4. I know that should equal square root of 2 over 2. I go over here. I put a dot. Oh my, can you see this? If I do that, I gotta make sure I reset. Okay, so then of course, if you notice the pattern, the dots align. So this one will be right here. Because cosine of pi over 3 is 1/2, right? And cosine of pi over 2 is what? 0. Let's connect these dots. Let's see what we get. Oh, come on. Oh, dots. Notice that we're actually going to get a wave again. Because whenever you go to, let's say, 2 pi over 3, the values of cosine become what? This is a negative 1/2, right? So cosine of 2 pi over 3 is a negative 1/2, correct? Yeah. So then now this wave continues like that. And so the wave is actually going to do this. That's a cosine wave. Isn't it amazing that the circle, cosine relates to a circle, the x values of a circle. Isn't it amazing that this correlates to a wave-like structure when we graph it? One type of interpretation is that got another hair tie over here. One type of interpretation is that, okay, it's as if you got the circle, all right? Break it, cut the circle, now twist, and then you got a wave. See that? And then you just copy and paste, and you create wave after wave after wave. Better save this. Better not forget this. Okay. So we've discussed the domain of sine and cosine. We've discussed the range. Now let's discuss an interesting property called period. These functions, sine and cosine, notice that they repeat, don't they? This pattern repeats. Functions that repeat are called periodic. Meaning, if you start at this value, if you wait some period in time t, eventually the function will repeat that value. This is not sacred for just one. It's actually true for any point on the graph. If you start at some point, if you wait some time, the period, it'll repeat in value. So this distance t, so this distance that I've drawn from here to here, which is the same as this distance that I've drawn from here to here, this is called the period of the graph, the period of the function, okay? So just right off the bat, what do you guys think that the period of cosine is? One really cool way to see it is that a period is also so you may be asking, okay, what about that distance? Well, that would be half of a period. You'd have to wait until the graph was back on the down end. So a period is basically a full wave cycle. So the graph has to go below and back on its way up to repeat that cycle for it to be the full period, if that makes sense. Here, from here to here, it's only like a half period because the periodic nature is that it goes up and then it goes down and then it starts to repeat. It goes up and then down, up and then down. This is just halfway. This is up and we stop. It needs to go up and down, boom. So at this point, this distance is truly the period. This distance we highlighted would be half of the period. So what would you guys say that the period, I should not delete that, I should delete these things. What would you guys say that the period of sine is? And what would you say that the period of cosine is? Let's start with cosine since the graph is up there. What do you guys think the period is? 2 pi. Yeah, that's correct. Because after 2 pi radians, the values just repeat. I mean, that right there is why we can say that, like, the sine of any theta is equal to the sine of that theta plus a 2 pi. Same thing. Also, the cosine of any theta is the same thing as that cosine of theta plus a 2 pi. Oh, so I just actually revealed that what the period of cosine is, didn't I? I kind of just blurted it out there. The period of cosine is also 2 pi. We've actually been using this property when we wanted to know, what is like cosine of negative pi over 3. We added a 2 pi to this and then said, oh, cosine of negative pi over 3 is the same thing as 2 pi plus negative pi over 3, which is 5 pi over 3. And then we said, okay, that's the same thing because it lands in the same spot. We have been actually using this property that cosine is periodic, but we never talked about it, that was what it was. We were just using its periodicity and not really acknowledging that, hey, periodicity is a thing. Let us define this phenomena that we notice in the mathematics. So now we've just explicitly defined the phenomena. So those statements right there, for Kinsey's sake, I'll rewrite them. That the sine of theta for any theta is the same thing as the sine of theta plus a 2 pi. Okay. But guys, let's not kid ourselves. There's nothing sacred about positive 2 pi. This is also a true statement, is it not? Yeah. if you think about it. Oh, but then this is also a true statement, is it not? Is it not? That's true. But this is also a true statement, is it not? But this is, now we're just almost getting borderline pedantic. But this is also a true statement, is it not? Right? Because this is just a multiple of 2 pi. One, two, three, four, 5. We know any multiple of 2 pi, either positive or negative, will land us in the same spot. So sine of theta plus, what is this number? 200,000 pi is the same thing as just sine of theta. I could have even said minus 200,000 pi, and it's still true. So how can we represent this trend in a concise mathematical way? We suggest as mathematicians that you say that this is true, that the sine of theta is the same thing as sine of theta plus 2n pi, where n is an element of the integers. This just means n is an integer. Who can give me an integer? Spit one out.
One.
Yep, that's an integer. Give me another one. 2, that's an integer. Very good. Don't forget the negative numbers. -3, that's an integer. So I can set this equal to any integer. Let's pick -3. That means sine of theta is the same thing as sine of theta minus 2 times 3, which is 6 pi. See, the way we wrote that out, it allows us to encode this phenomena that we're seeing here in a mathematical way. So n has to be an integer. Once n is an integer, this always works. Also, n can equal 0, and then you trivially get sine of theta is equal to sine of theta. Isn't math cool? Math is really cool. I don't know who's been lying to you guys. Math is really, really, really cool. Okay. Furthermore, the same token allows us to say that this is true. So don't forget these facts here. That the period of the sine and the cosine function is 2n pi. Okay. We've been doing that. Okay. Your book talks about increasing and decreasing. Let's talk about what that means. Increasing and decreasing. So since cosine is more fresh in our minds, here's the graph of cosine. This is at 1. This is at -1. Clearly, it crosses the t-axis of pi over 2. Clearly, it then becomes 0 again. at 3 pi over 2. Clearly, it's negative at pi. You guys see what I'm saying? Okay. So, the textbook we have talks about increasing and decreasing portions of a function. So notice that the function at this point here, its values are constantly decreasing. They start off at 1, and they just keep getting smaller and smaller and smaller until some point here where they don't get any smaller, right? So we say that the circles here, this circular region, is a decreasing. It's a decreasing region of the function. The function is decreasing. And actually, we can say that it's decreasing on what domain? Well, 0 to, where is this? Pi. To that domain, it's decreasing. But, oh, what happens here? Now everything's looking different. I'm hoping that looks different. I'm gonna try zigzags. Oh, I should have just tried zigzags at first. Either way, you can tell that they're distinct from the circles. Notice from this region, from this point on to here, the function is increasing in value because it starts off at -1 and just keeps getting bigger and bigger and bigger, and this is the apex, the highest value it assumes. So over here in this region, it is increasing. And what is it increasing on? Okay, we could just say it's increasing on. Where did this start? Pi. Where did it end? Oh, we haven't even said where does that end? Where should that end? What is this point right here? This mystery point. Where cosine again becomes 1. Yes, sir. That is correct. So this cosine function, oh, actually, so does the sine function. They go through periods of decreasing and increasing, decreasing and increasing, decreasing and increasing. I mean, that's what makes a wave, doesn't it? The wave goes up and it comes down. And it goes up and then it comes down. That's what a wave is. Okay, so your book talks about that. So get good at talking about, you know, analyzing a graph and see where it's decreasing and say, okay, it's decreasing on this interval, it's increasing on that interval. With graph sine, with graph cosine. Oh, beautiful. Now it's time to do graph transformations. I really wish I had a different color chalk with me. I usually come prepared. I think some people, maybe I didn't bring any colored chalk with me here. Took my colored chalk. I have some in my office. Okay, aha. So before we get to graph transformations, and it's wonderful that time actually will allow us to get to everything today, as it should. Let's talk about the even and odd property of sine and cosine. All right. So let's talk about what it means for a function to be even. A function f of t is an even function if, here's the condition, f of negative t is equal to f of t. Let me give you an example. Let's say f of t is equal to t squared. I will prove to you f of t is even. I will do so by evaluating what is f of negative t and show that f of negative t is the same thing as just f of t. F of negative t is what happens when I replace all the t's here with a negative t. Right? So negative t quantity squared is just negative t times negative t. Which is what? Positive t squared. Oh, but look, by definition, positive t squared is t. Oh, we just proved f of t is equal to t squared is an even function. Because f of negative t is equal to f of t. Here's another example. F of t is equal to t to the fourth plus t to the sixth minus t squared. This is an even function because f of negative t is this. Okay? But when you raise anything to an even power, it undoes the negative and just gives it that power. I know what you're thinking. Why is that minus sign there if it undoes the negative power? Well, or if it undoes the negativeness. Well, it undoes the negativeness here. That minus sign was always there outside the parentheses. That's why that's there. Notice that t to the fourth plus t to the sixth minus t squared is the same thing as f of t. So indeed, this function is an even function. All right. Time to show you that the cosine function is an even function. I will prove to you cosine of t is even. You guys want geometric or numerical proof? Or both? Here's your cosine of t, right? To show that cosine of t is even, we must show that the cosine of negative t is the same thing as cosine of t. Anthony already started to notice this trend when he said, oh, well, cosine of negative pi over 3 should just be the same thing as cosine of pi over 3. Remember that? Remember when you said that? You already were, without even knowing it, noticing that cosine was an even function. Because what is a cosine of pi over 4, for instance? 2 over 2. Oh, but look. You guys see that? It's also, cosine of negative pi over 4 is also root 2 over 2. Oh, but I mean, to show that it's truly even, we have to show it's even for all t, any t, not just pi over 4. Notice that we didn't even have to call this pi over 4. it could just be t and negative t. We notice that the output over here is cosine of t. And cosine of t is equal to cosine of negative t in height. This distance here is the same. Therefore, geometrically, cosine of t is even. What does this get? What does this buy us? You guys don't have to do this on your test. I'm just showing you the beauty of math. Here's what you should remember for tests and homework. That if you ever get something like this, you can automatically assume that it's this. If you get something like this, you can automatically assume it's equal to this. If you get something like this, you can automatically assume it's equal to this. Isn't that great? Because dealing with negative angles is a pain. We don't really have an intuition for negative angles. We only have an intuition for their positive counterparts. Notice that this information wasn't revealed by just adding the 2 pi to this negative angle either. It wasn't revealed right off the bat. So this is what cosine being an even function buys you. Let's talk about sine being an odd function. Before we talk about sine of t being odd, let's talk about an odd function in general. I know what you're thinking. Professor Niazi, you're an odd function. That's true. I am an eccentric individual. Please don't make fun of me. Do I have any, like, you know, those notes on the back that says kick me? Okay, good.
Did you?
Did I?
Yes. I'm just asking.
That should just be a rhetorical question.
So no.
Huh?
So no.
No, you should just know that whether I got kick me signs or not. Did you guys do that growing up? Put kick me signs on people?
No.
You guys were more mature than my classmates.
We're in a different era than you.
Yeah, it's my era kind of stuff.
If we did that, we would literally get expelled.
That's
It's pretty bad.
crazy.
It's a bunch of pacifists.
I wish I had that kind of protection. Okay, so let's talk about a function f of t being odd. Because sine of t is a function f of t. F of t is odd if, here's the if, f of negative t is equal to negative f of positive t. Dun, dun, dun. What does this mean? Let me give you an example. What if f of t is equal to x cubed? Oh, that makes no sense. T cubed. We prove that this is an odd function by analyzing what is f of negative t. Well, f of negative t is negative t quantity cubed. And then when you cube a negative number, it becomes negative t cubed. You guys see why? The reason for this is that this is negative t times negative t times negative t. This becomes positive t squared times the negative t. That times that gives us this negative t cubed. It's the same. Oh, but negative t cubed is the same thing as negative f of t. We've shown that t cubed is an odd function.
Can you move your water bottle, please?
Oh, yes, sir.
Thank you.
You can then go show on your own that f of t is equal to x is an odd function, and f of t is equal to x cubed plus x to the fifth is an odd function. X, I mean t's. You guys could go show it to yourselves. What I'm going to show you is that sine is an odd function, meaning that sine of negative t is equal to negative sine of t. I'll do so geometrically and a little bit numerically, because you just kind of have to. Remember that the sine function looks like this. Here's 1, here's negative 1. Right here, it assumes that positive 1 value at pi over 2. Right here, it crosses the t-axis, it becomes 0 at pi. Right here, it becomes negative 1 at 3 pi over 2. And then it recrosses 0 at 2 pi, right? Okay. Notice that at negative pi over 2, it's equaling negative 1. Let's take that as our point of interest. And so let's analyze here, and let's analyze here. This distance is negative 1, is it not? This distance is positive 1, is it not? This distance is positive 1, this distance is negative 1. So what we're really looking at here is that the sine of pi over 2, which is 1, sine of negative pi over 2, which is negative 1, right? So let's then say that, okay, then that means that the sine of negative pi over 2, which recall is a negative 1, is the same thing as a negative sine of pi over 2. Because then this becomes a negative positive 1, which is a negative 1. So numerically, at least for the fixed value for t is equal to pi over 2, we've shown that sine is odd, it has odd behavior. But this is true for any arbitrary t. Let me pick t here. That means negative t would be here. Then for any arbitrary value, boom, boom, and boom, boom. Notice this point is sine of negative t. Notice this point is sine of positive t. This distance, if I drew it to scale, is the same as this distance. If I had a perfect sine wave, it would look exactly the same distance. If I had a perfect sine wave, I'm not perfect. Not perfect at drawing curves. But this distance is actually the same as this distance, except this is going in the positive direction. This is going in the negative direction. So what we can say is that sine of t if I put a, so what I can say is that sine of negative t, okay, sine of negative t, if I put a negative in front of it, it would flip its sign over here. So if I just put sine of t over here, it's not correct. Sine of negative t doesn't equal sine of t, because that would mean that it's going in this down direction. Sine of t is going in the up direction. So how do I bring this up down? I just tack a minus sign. And that's precisely why sine of t is odd. This is a geometrical proof and a slightly numerical proof. Okay? Okay? So, what does that buy us? This is what it gets us. Now that we've shown it to be true, what can you guys use in your homework and on your tests? Well, just know that if I ever ask you, what is the sign of negative 101 pi? You can say, oh, it's the same thing as negative sine of positive 101 pi. I know that. The negative pops out. Whereas for cosine, it eats the negative. Because cosine is even, but sine is odd. So after cosine eats the negative and it goes away. Sine eats the negative and ejects it outside of itself, if you will. That's one way to think about it. Now, I don't believe we have 5 minutes remaining. That is not enough time to justify this last piece of the section. Okay? I will assign the homework in this section, but I won't make it due in a week from now. So what's today? Tuesday? The homework for 4.1 will be due not the following Tuesday, but the following Thursday. Okay? Because on Thursday, I want to finish up this section and really do a bunch of examples because I want you guys to have a thorough understanding. But for the last 4 minutes remaining, I want to at least introduce you to the concepts that we'll be talking about Thursday. And this is the graph transformations of the sine and cosine graphs. Okay. So here's our standard form. Our f of t is going to equal to some a sine of bt minus c plus d. And you know what? I probably could use that monitor on Thursday to make the graphs look nice using computer graphing and not my very poor hand graphs. So let's talk about what all these letters mean. We'll discuss them, okay? A is the amplitude. Okay, when you have a sine or a cosine function, the amplitude is the distance between the two highest points cut in half. So what would be the amplitude of just normal cosine of t? Notice that cosine of t ranges from +1 all the way to -1. Notice if we add those two values, that's 2, because this is 1 and this is 1. 1 plus 1 is 2. So that's why we cut that total distance in half. So we say that the amplitude of cosine of t is just 1. So cosine of t just has amplitude 1. And that makes sense because notice that that coefficient in front of cosine of t is the number 1, which is equivalent to a. Next, let's talk about what does this b mean. This b allows us to define period. Period is equal to 2 pi over b. For sine and for cosine, the period is 2 pi over b. Meaning, if b is equal to 1, I restore the original sine or original cosine period of 2 pi. But if b were to be a different number, let's say 2, then the period of the function shortens. If b were to equal 2, the 2's would cancel, for instance, and you get a pi. So the period would end up becoming a pi. Or if b was a 3, then the period would become 2 pi over 3. Basically, b allows us to modulate the period. And so on Thursday, when I do the really cool computer graphs on the projector, you'll see that, hey, changing that number b is going to make the graph, actually, it's going to make the wave happen either faster or slower based off of the number. If the number b is a whole number, then it's going to make the period happen faster. But if the number b is like a fraction, it's going to actually make the period happen slower. So what if b was 1/2? If b was 1/2, then it would make the period become 4 pi. So it actually makes the wave elongate. It stretches it out versus compressing it. Okay. What is this C? I at least can define these things before Thursday. This C is called our horizontal shift. Shift. We'll see what that means. Okay. Really, a horizontal shift is when you pick up a graph and translate it either to the right or to the left, horizontally. You pick it up and you put it back down. So our C is our horizontal shift. And last but not least, our D is going to be defined as our, you guessed it, vertical shift. Is it vertical or vertical? It's vertical. Vertical. You guys may go. You guys were very good today. Thank you so much. Oh, it's vertical. I had it right. Oh, and I changed it to the right one. Guys, I don't want to seem too soft, but if any circumstances occurs, like life circumstances, you know, COVID circumstances, whatnot, and you can't turn your homework in on the scheduled time, just let me know and I can provide you extension. Just do not get in, you know, just don't just take that and run with it, because then your assignments would get very behind. But if there's any real issues that are preventing you from getting your assignments done on time, let me know and you guys will get extensions. Okay? I just want you guys to be successful.